Hello everyone. So this is the first of my videos for chapter 5. I will try to keep it very short, so it will only be about section 5.1. So in cosmology, we try to find expressions for the energy density, the pressure, and the scale factor of the universe as a function of time. And in this chapter, we actually find these expressions for various model universes, for simplified universes. But one of them, the benchmark model, actually we think closely corresponds to our own universe. Now to do this, we are going to be using these three basic equations: the Friedmann equation, the fluid equation, and the equation of state. So these were all derived in chapter 4, but we're also going to be using some results from chapter 3 as well. So when you look at these equations, and so these are three equations for three unknowns, and you want to solve them for this epsilon, p, and a. Now the first thing that might occur to you is just take this third equation and substitute into the second one, and hence eliminate this p, and then you get two couple differential equations, and you try to solve them this way. Now this looks fine. However, there's a problem here, that there is no single value of w, right? So this is an equation of state for a given component of the universe, and for non-relativistic matter, this w is going to be 0. For radiation, it's going to be 1/3. And also for relativistic particles, it's going to be 1/3. And for dark energy, it's going to be less than -1/3. In particular, for cosmological constant, it's going to be -1, right? But there is no single value, so you can't just go on just solving those two coupled equations. So what you do instead is that you try to solve these equations component-wise for each component. And to do that, what you do is that you assume that the components do not actually interact with each other, right? So first thing you do is over here, so you write your energy density as a sum of the components of the energy density of the component, and then of course the pressure is going to be just the sum of the pressures of different components. Now if the components do not interact with each other, then you can write this fluid equation for each component. Now why? Because if the components do not interact with each other, you can actually write the first law of thermodynamics for each component, and then you can solve it for each component, right? This change in internal energy is equal to heat minus the work done. If the components are not affecting each other, if they are not transferring heat to one another or doing work on one another, it's going to just work for each component separately, which means that you can write the fluid equation, which is based on first law of thermodynamics, separately, right? So you write it for a given component. This I denotes the component. It could be radiation, matter, whatever. And then you make this substitution that for each component your pi is going to be wi times epsilon I, and you take into common parentheses and you get this, right? And then you rearrange this. So this is actually d epsilon I by dt, and this is dA by dt. And then you do this, physicist trick that mathematicians do not really like, but you just multiply everything by dt, right? You treat the derivatives as a ratio of differentials, something like that, and you get this expression, right? Now the left hand side depends only on epsilon or epsilon I. The right hand side depends only on a, which means you can actually integrate this differential equation, and when you integrate it, you get this exponential dependence, right? And so far we didn't actually use the Friedmann equation. This is solely based on the equation of state and the fluid equation for a given component, right? Now, but this already tells you how your energy density is going to change given its initial value and given some value of the scale parameter. So if the scale parameter changes, your energy density is going to change in a particular way. So we know the value of this W for a number of components. So for example, for non-relativistic matter, W is just 0. So for non-relativistic matter, the energy density is going to scale as the initial value divided by the scale parameter cubed. Whereas for radiation, this W is going to be 1/3. So the energy density for radiation or relativistic particles, it's going to scale as the initial value divided by, I shouldn't say it's initial value, the present value divided by the scale parameter to the 4th power, right? So now why do we have this difference between the radiation? It is shown schematically in this figure over here. So as the universe expands or just contracts, as it changes volume, as this the scale parameter changes, the number density is going to change. Let's say that it expands, so the number density of the matter and the radiation is going to decrease, proportional to the volume of the sphere that you're taking, right? So it's going to be the number density is going to decrease as a cube for both of them. Now for matter, this is pretty much the end of the story. But for radiation, what is going to happen is that you're going to have an additional redshift. So the photons are also going to sort of expand, and their wavelength is going to change, which leads to a change in their energy. Right? As the wavelength gets larger, the frequency and the energy is going to decrease. Now, by how much? Well, the wavelength increases in proportion to scale parameter, and so the energy is also going to decrease in proportional to scale parameter, right? Or inversely proportional to scale parameter, let's say. So, and this brings this additional factor of 1 over A. So, even though the number density of both these components, matter and radiation, drop as 1 over A cube, the energy density is going to decrease as 1 over A4 for radiation and relativistic particles. Now, so when you say this, when the number density is conserved, you're of course assuming that no matter is created or destroyed, or no radiation, no photons is created or destroyed during the evolution of the universe. Now, the first one is pretty correct, right? If you there was some matter creation and destruction at the beginning of the universe, but then the rate of this is now very low. I know that the stars still produce some light, and they turn matter into radiation, and so on and so forth. So there is some actual interaction between these two components, but that's completely negligible. That's very small. And to see this, that you can actually estimate the radiation content of the universe with respect to the radiation that's created by the stars, right? And this is done, I think, over here. Before going on, you want to write these components in terms of the critical density of the universe, and so this is the present value of the energy density of the cosmic microwave background, and this is just Stefan Boltzmann law. You just get this number. Right? This critical value, when you divide this by the critical value of the universe, which you can deduce from the measurement of Hubble constant, you get this very small number. It's a very small contribution. Right? However, even though this is a very small number, the total contribution of the energy density of the cosmic microwave background photons, the total energy density is very small. This is actually very large with respect to starlight, because when you estimate that, the energy density of starlight turns out to be this very small number, right? So compare this to the cosmic microwave background photon energy density. This is 0.26 megaelectron volts per cubic meter. This is 0.006 megaelectron volts per cubic meter. Right? So you can completely neglect the starlight, which also means that you can completely neglect the destruction of matter, the formation of additional photons from matter in the stars. Right? You don't have to, of course, throw this away, but you can try to take this into account. But for our purposes, this is not going to be necessary. Right? But perhaps this is what you're interested in, and then you, of course, want to take this into account and see what the effects will be. Right? Okay. Now, in addition to photons, when we look at the radiation, we also need to take into account other relativistic particles, and one notable component is, of course, the neutrinos. Right? This cosmic microwave background is not coming directly from Big Bang, but it's coming from the time where the photons were no longer scattering of the electrons or scattering of the matter. Right? So initially, our universe was opaque, and the photons were continuously getting absorbed and re-emitted. But as the universe expanded, the density went down, and at some point, for various factors, it became transparent to these photons, and the photons we are observing right now are from that time. Now, something similar happens for the neutrinos. So neutrinos in a very dense universe would actually be captured and re-emitted continuously through beta decay and other processes from weak interactions, basically. But at some point, the universe is going to get so dilute that it's going to become transparent to neutrinos. Right? So by going through similar calculations, you can actually calculate the cosmic neutrino background, and this, if the neutrinos are relativistic, this is also going to contribute to the radiation energy density, right? Because they also are going to have a W parameter of 1/3, just like the photons. Right? If the neutrinos are slow, then they act like matter. Their W is 0, but if they are relativistic, then they are going to act like radiation. So we need to take them into account, assuming that they're relativistic. So when you carry out this calculation, then you find that the density parameter for those is going to be close to 70% of the density parameter of the cosmic microwave background. Right? If all neutrinos are relativistic, and if you have a certain number of neutrino flavors, and so on and so forth. So this it's actually has some assumptions. So their contribution is not going to be negligible. Their contribution to the energy density is not going to be negligible. So we write the total density parameter for the radiation in this equation 5.18 as the contribution coming from the cosmic microwave background photons plus the relativistic neutrinos. And this comes to, from theoretical calculations, to 9 times 10 to minus 5. And note that this is 9.00, so you can calculate this pretty accurately. Right, so these two numbers you can calculate accurately, but the rest of the components, the matter and the dark energy components, which we are going to assume is going to be just cosmological constant, is not so easy to estimate, right? But there are other additional observations that we use to estimate these numbers, and these favor the numbers of the benchmark model. So for the density parameter of the present value of the density parameter for matter, we estimate it to be 0.31, and for the cosmological constant, the current estimate is 0.69 almost. Right, so this is something very small. This is much smaller than 1, so these almost add up to 1. So with these four ingredients, so these 3 numbers plus that they should all add up to 1, we construct the so-called benchmark model. Right, so this is the model that we're going to use in this book, unless we say that we are looking at some model universe that deviates from this significantly. So these are the components. The density parameter for radiation, which includes not just microwave background photons, but also relativistic neutrinos. That is 9 times 10 to minus 5. The density parameter for matter is 0.31. That's the non-relativistic matter. Relativistic matter contributes to radiation. And the density parameter for cosmological constant is 1 minus the sum of these two, which comes to something like 0.69. Okay? So by definition, these all add up to 1. Right, so this is going to be our benchmark model. So in our benchmark model, we have 3 components, plus these add up to 1, so the curvature is going to be 0. But in general, we can, of course, allow curvature as well. Right? Okay, so taking these numbers, so these are the present values. Right? So this is all the numbers, all the estimates, they come from present values. And they are going to have a certain time dependency, 2 of which we have seen here. Right, so these are of course for the energy density, but when you divide this out by the critical value, you get the density parameter, so they actually, you can find out their time dependency in the same manner. Okay? So let's look at this time dependency. So in the present value, if you compare the present value of the dark energy to energy density in matter, so the ratio of energy density in lambda to energy density in matter, you should find something like 2.23. Right, so we say in this case that the dark energy component, or the cosmological constant component of the universe, dominates over the matter component because its contribution, its energy density, is more than twice as high. Right? However, these are the present time values, and they have certain time dependence. Right? So this epsilon lambda is the energy density of cosmological constant is just constant by definition. That's how cosmological constant works. So the time dependency, the time dependent expression for this is just again epsilon lambda 0. This one, however, changes over time. So the time dependent form for that is going to be the present value divided by a cube. Right? So if we write the time dependent version of the ratio of these two energy densities, we get a dependency on the scale parameter as a cube. Now we can set this to 0, so set this to 1, and see when these two contributions will be equal to each other, and solve for a, and that a is going to be called am lambda, and the value comes to 0.766. Okay. When the scale parameter had this value, this is in the past, so the current value of scale parameter is 1. In the future, because we are expanding, it's going to be larger than 1. Something smaller than 1 corresponds to the past. When it had this value, the contribution, the energy densities of the cosmological constant and matter were the same. So this is actually not too far off in the past. So we just passed this point, and in our universe, cosmological constant became dominant, and so we can actually see its effects. Okay? So you can do a similar calculation. So currently, the cosmological constant is dominant. When lambda was smaller, when A, the scale parameter, was smaller than this value, 0.766, matter was dominant. Right? At least it was dominant over the cosmological constant, so we can now compare it to radiation as well, whether it was dominant over radiation too. And we go through the same calculation. We write down the expression for the ratio of the energy densities, and we write these two as functions of scale parameter. Right? These scale differently. One scales as 1 over a cubed, the other one, radiation, scales as 1 over a to the 4. So you can write it that way, and then the ratio, the time-dependent ratio, is going to scale as is going to be proportional to a. You set this equal to 1, and by using the current values, we find that the radiation matter equality took place when the scale parameter was much smaller, 2.9 times 10 to minus 4. So between these two, 2.9 times 10 to minus 4 to 0.766, our universe was matter dominated. After this point, it was cosmological constant dominated. It is cosmological constant dominated, and before this value, 2.9 times 10 to minus 4, it was radiation dominated. Right? And there's some argument here about the neutrinos, that your assumptions still hold. Nothing is going crazy. And yeah. So now, as you see that I'm referring to eras using the scale parameter itself rather than attaching a certain time to these. Now, an alternative would be to refer to these using some redshifts. Right? So I can just, instead of quoting the value of A, I could just quote the redshift. And so anything, any signal that's coming with that redshift will be coming from that era. Right? And the relationship between the scale parameter and the redshift is given here. I think this was the end result of chapter 3. So 1 plus c is going to be equal to 1 over a. Right? So I can easily convert scale parameter to some redshift. However, it's not going to be easy to change this into some definite time, like in terms of years, and that's because to do that, you actually need to write down Friedmann equation in this form. So this is just Friedmann equation itself. You take your original equation, so let's go there. You take this, you expand this square, and then you multiply everything by square. So on the left-hand side, you kill the 1 over a square term. On the right-hand side, in the second term, you kill the 1 over a square term, but then you add an additional a square term over there. So you get this expression here, and then because of that a square, you're going to then write, you substitute the solution. Where is that solution that we find just purely by filling the equation at this thing here. You make your substitutions and so on and so forth, and you end up with this equation. Now you have to to convert your scale parameter into time. You have to solve this, right? And in principle, you can. These are just observables, and this is something you can measure or estimate. This epsilon is something you can measure or estimate from observations. So this is just a differential equation for a, but it's quite complicated. Right, so there are these different omegas and so on and so forth. So if you make some assumptions, some simplifying assumptions, like curvature is not there, and so on and so forth, you can solve this. But as you see, the conversion between the scale parameter and time actually depends on what model you're using. For the benchmark model, you can solve this only numerically. You can't solve it analytically. But for simple models, as we are going to see, you can actually solve it analytically, and that's going to tell us certain things about the current universe. The reason why we are actually going to look at these simple models is because of this dominance business. So there are these well-separated eras. So after 0.766, our universe is cosmological constant dominated. Between 2.9 times 10 to minus 4 and 0.766, it's matter dominated. And before that, before this 2.9 times 10 to minus 4, it's radiation dominated. So it makes sense to actually look at these. And as we are going to see, you can actually say something about the two-component universes as well, though the full solution of this equation is going to be beyond our reach. You can't do this analytically, but we are going to see how you can actually solve it numerically. Okay, so that's all for this section.